Homework 3.1, Quadratic Functions, Video 7. Homework due Wednesday, May 27th, 2020 at 11:59 p.m. The following video applies to question 16 on the homework. Applications, Part 1. Applications is a fancy way of saying let's use the math to solve a real world problem. Now that real world problem might be kind of artificial and made up, but I'll be honest with you. The math used for real world problems is calculus and beyond. When you do real world problems in algebra, they're either very limited in their application, or you're making a lot of assumptions. But the more real world math gets, the harder the math gets. So at this stage of the game, it's hard to say, here's a brilliant everyday example where you might use something. Don't get me wrong, they exist. But I guarantee you, if you look through any algebra book, college algebra, algebra 1, algebra 2, the majority of the word problems are either oversimplified or just aren't realistic. But you got to start somewhere. So for those of you going down the calculus path, you'll eventually learn more math to solve more realistic, real world problems. So let's take this one. Suppose you have 100 feet of fence. Why? Why not? And you're going to build a rectangular pen. What are the dimensions of a rectangular pen with the maximum area? Now, that's not a lot to go on. But we have two things that work to our advantage so far. We've got a known value called a constraint. We're working under the constraint that there's 100 feet of fencing. And we got another value that we're trying to maximize. The generic word for maximize or minimize is optimize, O-P-T-I-M-I-Z-E. And in calculus, you'll learn about optimization problems. But those are just problems where you try to maximize or minimize something, such as coming up with the maximum area. Now, before we jump into this, let's wrap our minds around some specific examples. For example, let's say that we make a pen like this, and let's just say that we decide to make this side 40 feet long. Now, if it's a rectangle, I know that the other side has to be the same dimension. But if we have only 100 feet, do you know how long each of these are? Hint, they're not 20 each. Because out of the 100, we've already accounted for 80 of the feet. So that means we have 20 feet left to share among these two sides. So we could have a 10 by 40 pen that's 100 feet around, but what would this area be? How do you even find the area of a rectangle? Oh, easiest geometry formula ever. Length times width, or base times height. So 40 times 10 is 400 square feet if you want to put a unit of measurement on it. I guess I should put feet on these. So there's an example of a pen that we could build, a rectangular pen that we could build with 100 feet of fencing, and its area is 400 square feet. But can we get a bigger area? What if we made it 30 by 20, 20, 30, 20, 30, that adds up to 100. But what's the area of this one? 20 times 30 is 600. Wow. By shaving 10 feet off of the long sides and adding them to the short sides, we picked up an extra 200 square feet. But how big can we make that area? What does your intuition say? Does your intuition say, well, obviously you should build this shape, and that should give us the largest area? At the end, you might go, oh, yeah, that makes sense. But yeah, okay, so how do we solve this? Algebraically, as opposed to numerically, where we just guess and hope we get the right answer. Well, the way you solve things algebraically, and this is one of the reasons algebra came into existence, at least from an application perspective. You're trying to find something you don't know. So you give it a generic name like x, and then you set up some sort of equation to solve to figure out what it equals. So how would we attack this generically? Well, let's start with a rectangle. And I need a generic number to represent this length. Let's just call it x. But where else could I put an x? Up here. Okay, that part's not too bad. But what should I call these other two sides? Now I could bring in another letter. I could say, we'll call this y. We could use L and W, but let's use X and Y. But think about how we figured out the other side when we had a number here. For example, when this was 40, why did this end up being, where did this 10 come from when this was 40? Well, when this was 40, we had two sides that added to 80. So we said 40 plus 40 is 80. And that meant that there was 100 minus 80, which was 20 feet left. Well, we had to divide that by 2. So could we do the same thing, but replace the 40 with an x? Well, x plus x is 2x. That represents these two sides. So if we take the 100 and subtract the 2x, that's what's left. But those aren't like terms, so I can't do anything to them. If you think you divide both sides by 2, don't. I'm not solving an equation. I can't randomly do things like that. I can factor out a 2, but I don't think that's going to be very beneficial. So if we take the 100 and subtract what we've already used, it gives us what's left over. And then we take what's left over and divide it by 2. Oh, we can split this into two fractions and reduce each one. 100 divided by 2 is 50. 2x divided by 2 is x. So it looks like if I put an x here, I put a 50 minus x here. And here, does that work? Well, it's a rectangle, and we have 100 feet of fence. So we need to make sure that it's a rectangle and we're using 100 feet of fence. Okay, it's a rectangle, assuming right angles, because these two sides match and so do those, but do they add up to 100? Yeah, they do. Because when I add these, the x's cancel, leaving 50. And when I add those, the same thing, and 50 plus 50 is 100. So it's actually a pretty good setup. But where do we go from here? Well, the next thing we did when we knew the numbers is we calculated area. But how do you calculate area? Length times width. This times this. This is starting to look like a function. So let's put it in function notation, but I'm not going to call it f of x. That's so generic. I want something a little bit more contextual. Let's call it a of x. Yeah. And why don't I distribute this? 50x minus x squared. Oh, this is a quadratic function. Let me write it in the order I would normally see it. I would normally see the x squared first, and it's negative, and the 50x second, and it's positive. So wait. I know what this graph looks like. I'll get more details in a moment, but A, it's a parabola, and B, it opens upside down. So another graph of this looks like that. The input is the x, and the output is A of x, which represents the area. And I'm looking for maximum area. Well, where on this parabola does the area be the highest? Right there at the vertex. So I think I've got a plan of attack. Now that I have this function, and honestly getting this was the hard part, if I find its vertex, the x-coordinate will represent this length, but the y-coordinate will represent the maximum area. So let's find and interpret the vertex. I erased the formula for it for the picture over there, but the formula for the vertex was negative b over 2a. The b is the coefficient of the x, so negative 50. It was 50 and I put a negative on it, over 2 times the coefficient of the x squared. Well, the x squared, the coefficient of the x squared is negative 1, and 2 times negative 1 is negative 2. Negative 50 divided by negative 2 is 25. Let's see what happens when we put 25 into the function. We get the opposite of 25 squared. Be careful, the negative is not being squared. This negative happens after the square. Plus 50 times 25. I happen to know that 25 squared is 625, and this one picks up a negative. And 50 times 25 is 1,250, or 1,250. And if I combine those, I believe I get 625, which means the coordinates of this vertex are 25, 625. So now I know the answer to one part of the question, because I'm being asked what are the dimensions, plural. I know the x is 25, is one dimension. What's the other dimension? 50 minus x, so 50 minus 25. Oh, that's also 25. So one dimension is 25, and the other dimension, which we only called 50 minus x, we never called it a different letter, is 25, giving us a largest area of 625. Did your instinct say earlier, make a square? Well, in this case, you would have been right. But not all make the biggest pen areas are squares. This one happens to be. So let's quickly recap what happened. And in the next example, you'll see why it's not nearly as bad as this one. But we were given 100 feet of fencing to build a pen, and we want the largest rectangular pen. Try that again. We were given 100 feet of fencing to build a rectangular pen, and we want to know what dimensions give us the largest area. Since we didn't know either of the dimensions, we generically called one of them x, and the other one ended up being 50 minus x, which in retrospect actually makes sense, because if there's 100 feet all the way around, and the bottom, and this part is half of it, and that part's half of it. So this is 50 feet, so 50 minus this gives us the other one. Then from that, we built a function that measures area based on what this is. That function ended up being an upside down parabola, one that opens downward, whose vertex is a maximum and tells us when the maximum area is and what the maximum area is. We found the vertex, it was 25, 625. The 25 told us this dimension, and then we subtracted from 50 to find the other. And by the way, 25 times 25 is 625. So that's the biggest area we could get. But don't just think it's always a square. In the next and final video, I'll show you an example where it's not.